how you do it.
No matter what process you do, you cannot violate this. Otherwise, Planck would roll in his grave. And then they relate the Kelvin statement and the Planck's proposition. And then they keep going, Planck's principle. After that, it probably, we don't need to read all of that. The second law in chemical thermodynamics. You've probably heard of maybe the Gibbs free energy, right? For a spontaneous chemical process in a closed system at constant temperature and pressure without non-PV work, the Clausius inequality, delta S is greater than Q over T, transforms into a condition for the change in Gibbs free energy. Delta G is less than 0. So delta S is always greater than 0, delta G is always less than 0. Opposite, right? For a similar process at constant temperature and volume, the change in Helmholtz free energy must be negative, delta A. So there's other quantities that are related to entropy that also when entropy goes up, something happens to them, and that always has to happen. So they're saying Gibbs free energy and Helmholtz free energy must always decrease. Okay? Then of course we can read about what those are, but I don't want to sidetrack. This is the most useful form of the second law of thermodynamics in chemistry, where free energy changes can be calculated from tabulated enthalpies of formation. You do that in Chem 102? And standard molar entropies of reactants and products. So sweet. Oh, great. And then they go into the history. Okay, now all the math starts. All that was just history and fluff, right? But then you can't avoid the math. So here we go. Statistical mechanics, a lot of partial derivatives. Sweet, sweet. Living organisms, gravitational systems. Arrow of time, remember how I said the arrow of time? Why does time flow from past to future and not future to past? Only in Benjamin Button does time go from future to past. His life went backwards, but the rest of us is always that way. Oh, and then keeps going and keeps going. Okay, good. Okay, now for the rest of the next thing let's do, let's apply entropy to non-thermodynamic problems, non-thermodynamic situations. Not necessarily gases doing work and isothermal, isobaric, those things, but let's just say a piece of ice sitting on the table. When I wait, after a while, the ice will melt and warm up, right? Let's calculate the change in entropy of the ice and the change in entropy of the universe, and let's see what that's equal to. So I'll call this non-thermodynamic types of problems. Entropy applied to non-thermodynamic type problems and probabilistic problems. Probabilistic problems. So let's say something like this. So let's go to that cube of ice. You put 1 cube of ice at -5 Celsius, and let's say the temperature of the atmosphere is 20 Celsius. So the atmosphere is your hot reservoir, and in a cold reservoir is the the ice, right? So over time, if you wait long enough, the ice is not going to get cooler. It's actually going to warm. It's going to melt. And finally, it's going to reach the same temperature as the atmosphere. The atmosphere might cool a bit, but not that much, because the atmosphere is a huge reservoir, right? So after the ice melts, and reaches 20 Celsius, what is the change in entropy of the ice? B, what is the change in entropy of the environment? And then C, what is the change in entropy of the universe? Okay, so then what's the change in entropy of the ice? Delta S is equal to what? dQ over T, right? What's dQ? Well, the heat that you put into the ice only goes into melting it, right? It doesn't expand considerably. So it's just going to equal mass of ice, specific heat of ice, times the change in temperature of ice, right? Plus, when it finally reaches 0 degrees, it has to melt, right? So M of ice times the LF. So this is back to chapter 19, chapter 20, I think, the specific heat chapter. Plus mass of ice, specific heat of water, delta T, divided by the instantaneous temperature of the ice. So then what's happening is as the ice is warming, its temperature also changing. So a small increment of the heat is not going to cause the same amount of change in entropy, right? Because the T is changing, right? So this is actually an integral problem. I have to say M ice, C ice, dt over T plus M ice, LF over T plus M ice, C water, dt over T. Then integrate this, right, from between what? The initial temperature and the final temperature of the ice, right? So what's that going to be? -5 Celsius to 0 Celsius. Can I do it in Celsius, or do I have to do it as Kelvin? Well, there's a dt. That one you could do in Celsius, but there's a T. Because if the T, you put 0 here, what does that mean? Infinity? You know? So you have to do it in Kelvin. So cannot do it in Celsius. So that's going to be what? 273 minus 5? 268.15. 273.15. And then so in the warming of the ice, that's how much the entropy of the ice is increasing. So what's the mass of the ice? 1 kilogram. Specific heat of ice is what? Remember, it was about a half of the specific heat of water, 2050 joules per kilogram per Celsius. 2050. And then ln of right? So mass of ice, specific heat of ice times this. But then here, do I have to do integral? Here is just the melting. How much heat is coming in is this. But the temperature is not changing as I'm melting it. It's staying at 0 degrees Celsius. So this is a non-integral one, right? 1 kilogram times the heat of fusion of ice is what? In joules per kilogram. Something like 300 something?
says H2O. That's
331
331.46.
joules per kilogram, and then this is kilogram, right? So yeah, that's it. Divided by the temperature when it's melting is 0 degrees Celsius, right? So then you're going to have here, so that's 273.15. And then the mass of the ice is going to be same thing. Oh, this one is also going to be an integral because after it melts, it has to warm up, right? So mass of ice, 1 kilogram, times the specific heat of water, which is 4,184 joules per kilogram, right? And then ln of what? Now it's going from 0 to 20 Celsius, right? The ice is going all the way from 0 all the way to the atmospheric temperature. So then that's going to be ln of what? 293.15 over 273.15. So that's how much, in all this process of melting, that's how much entropy the ice is gaining. This is going to be one of the biggest change in entropy of the ice because change of phase is huge. It goes from solid to liquid, its entropy goes crazy. This is the biggest number. The next biggest number is going to be this because the ratio of these two is less. But this is small. Okay, that's small. This is double that. But the ratio of these two is not as big as the ratio of these two, right? So we add this all up and we get the answer. So let's see what that comes out. $334.74. That's joules per Kelvin, delta S of ice. Okay? Now what's the delta S of the environment? How do we do that? How much heat did the environment lose? How do we do that? Well, where did this heat that went into the ice come from?
The environment.
It came from the environment, right? So this top portion of the equation, the M ice delta T plus M ice LF, M ice CF delta T. But the only difference is that all along, the temperature of the environment didn't change. So the bottom is what's different. But the ice, as it was heating, the temperature was instantaneously changing. The atmosphere, it stays the same. So the change in entropy of the atmosphere is going to be what? M ice, C ice, delta T over plus M ice LF plus M ice CW delta T over T atmosphere. And in your mind, you're probably thinking, well, aren't those going to come out the same? Delta S here is going to come out negative 334, right? Because it's losing the heat. It's the same amount of heat that it's losing, and the ice is gaining the same amount of heat, right? Shouldn't they cancel? Well, if they cancel, that means the delta S of the environment is negative 334. No way. Because the temperature of the environment is what?
Constant.
Constant, and it's bigger. This number is bigger. That number is bigger and the top is the same, what's going to happen?
It's gonna be
If you have a
smaller.
bigger number, it's going to be smaller. So this is going to be something like negative 320. When you add them, what's the change in entropy of the universe? Positive. If it was 0, that's dangerous because that means this process can instantaneously reverse itself and go in the opposite direction. This cannot be negative 334, right? So let's put in the numbers. 1 times 2050 times what's the change in temperature of the ice? 5 Celsius or 5 Kelvin. Because now since it's delta T, I could use it as 5, as a Celsius. Plus the M ice times LF. Okay. Plus M ice times 4184 times what's the change in temperature of the ice? 20. Over what's the temperature of the atmosphere? 293, right? Ha ha ha, look what's going to happen. As the atmosphere is hotter, right? So its change in entropy is less. Remember, what did we say the first half an hour of the lecture? When something is hotter, the same amount of equivalent heat loss or gain is not going to change its entropy as much. It's like the disorderly friend that you have. Negative 321. That's the way the universe works, guys. So the change in entropy of the universe is positive.
So you convert it to Kelvin?
Oh, because it's T.
Yeah.
T. Delta T is okay,
Okay.
but not T.
Okay.
Yeah.
Alright.
So delta universe 3 to the 34 minus 321. Now, can I reverse this process? Yeah, you can take that ice, put it back in the fridge, right? And then now suck out the heat from the fridge, from the ice, cool it back down to 5, but in doing so, what are you going to do, the fridge? It's going to dump heat back to the atmosphere. So if I go down, I'm still not going to go back to 0. It's the entropy of the universe is always going to increase, right? So I'll come back to this problem later when I do a refrigeration next Wednesday, right? Now let's go to one of the problems we did. Well, you know what? Let's just do a fresh problem. Calorimetry problem. So, calorimetry. So you say, let's say you put a hotted, let's say imagine this is a calorimeter, right? You take water, 200 grams of water, H2O, at 20 Celsius, and then you put in here 150 grams of aluminum at 100 Celsius. This is kind of one of the labs we do actually. Oh, didn't you guys do this lab yesterday? I saw you guys doing the calorimetry. You had the temperature?
Thermo expansion.
Have you done this lab?
No.
No.
Mixing the hot metal with the water? Physics 11 does it, right?
Yeah.
And then you mix it, then you wait till it reaches the temperature, right?
Right.
You say, oh, this is going to lose heat, this is going to gain heat, they're going to finally achieve the same temperature, right? So now tell me, if you mix this aluminum with this water, find the final temperature of the mixture and find the change in entropy of the universe as a result of this calorimetry problem. Find TF and delta S universe. So to find TF, we use the techniques that we learned back in chapter 20, right? The heat gained by the water is equal to the heat lost by the metal. So how much heat did the water gain? Mass of the water, specific heat of the water is 1 calorie per gram, TF minus 20. To do the calorimetry problem, I can do it in calories. I don't need to be joules. But then to do the delta S, I'll do it in joules, right? So this is the heat gained by the water. The heat lost by the metal is what? 150 grams. What's the specific heat of aluminum? 0.215, right? Remember, if you've done that lab, 0.215. Calories per gram per Celsius. And then what's the delta T of the aluminum? Should I do final temperature minus initial or initial minus final? TF minus 100 or 100 minus TF? 100 minus TF, right? You do it so that it's positive. Positive equals positive. Then you multiply that in. Multiply this in, well, that one is a bit harder. $3,225 minus 32.25. And you go over here, this one goes over here. So 232.25 TF is equal to 7,225. $31.08. 31.08. So notice the metals lost some heat, the water gained some heat, equivalent. But which one's change in entropy is more? The water's increase in entropy or the metals decrease in entropy? The entropy, not the heat. Which one is warmer to begin with?
The metal.
The same amount of heat lost from the aluminum should not affect its entropy as the water, because water is more orderly. If it gains the same amount of heat, it's not going to get as disorderly, right? Its temperature is lower. So that means the change in entropy of the universe is positive. I'm assuming the calorimeter is perfect vacuum so that no heat exchange to the atmosphere in this problem. It's a perfect vacuum. So the atmosphere is not losing heat or gaining heat. It's just between the metal and the water, right? So how do we do the change in entropy of the water? dq over T. So that's what's going to be. dq is going to be mc dt over T. So it's an integral again. Mass of the water is going to be 0.2 kilogram. Specific heat of water, 4,184. Now I'm doing it in joules and kilograms, right? So I'm changing the mass of the water to kilogram times ln of T final over T initial, right? It's an integral of this. So T final is what? 31. Convert that to Kelvin, right? Let's see, no. 304.23. Divided by its initial temperature is what? 293.15. There you go. That's the change in entropy of the water. Th- 31.04. Change in entropy of water, 31.04 joules per Kelvin. What's the change in entropy of the metal? Minus m of the metal, C of the metal, or I don't even have to put the minus, times dt over T, right? But then this is T initial is gonna be what? It began at 100, so that's 373. And then what's T final? Well, the T final is the same as the T final of this guy. They both reach the same temperature, right? 304.23. So now what's the mass of the metal? 0.15 kilograms. What's the specific heat of the metal? It's 0.215 of the 1, right? It's a ratio of 0.215. So the specific heat of the metal, 0.215 times 4184 times ln of 304.23 over 373.15. Now I'm a little bit worried here because this number 0.215 is going to make this small compared to that, right? This is 0.2, this is 0.15, so this is already smaller mass. The specific heat is 0.215, that makes it really small. So is it possible that this comes out negative and smaller than 30, let's see here, smaller than 31? Oh, no, yeah, that is actually good. It's actually good that it's small. I shouldn't be worried. Oh, but then this is worrying me. The change in temperature of the ice is, of the metal is big. That worries me. The fact that this is small is actually a good thing. So now let's do this. But the universe says, don't worry, I'll take care of you. I got you on this one. ln. The ln of this comes out negative. (31 negative 27). You see? So even though this was bigger, this thing and this thing worked it out. So the delta S of the universe, about 4 something, right? Approximately 4. Okay, now the universe says, I got you. You see, the entropy of the system increased. Now, can this system spontaneously go backwards? The metal heat up and the water cool down? No, it's never going to go the opposite way. But if you wait long enough, it might. But it just takes infinite number of years. You know, it's highly improbable. Okay, guys, very good. So next Wednesday we'll continue it. But for now, Monday is the test 4.